All right, let's get into something truly mind-bending today. What happens when you take one of the most powerful tools we've ever created, artificial intelligence, and aim it at the biggest mystery of all, the fabric of space-time itself? We're talking warp drives, we're talking wormholes, and yeah, we're talking about the insane possibility that AI could actually help us rewrite the fundamental laws of the universe.
So, let's start with this quote. The Alcubierre warp drive. I mean, this is the stuff of our biggest dreams, right? For as long as we've looked at the stars, we've wanted to go there. And this isn't just some fantasy from a movie, it's a real, honest-to-goodness scientific proposal. Think about it, getting to Alpha Centauri in a few weeks instead of, tens of thousands of years, it's an absolute game changer.
But here's the big question. Is it just a dream? Because for a long, long time, that's exactly what it felt like. The physics behind it, well, it seemed to break all the rules. We're talking about energy needs that are just astronomical and materials that, well, they just don't exist. It was this beautiful concept, sure, but it felt like it was stuck forever in the realm of science fiction.
Okay, so how does this thing even work in theory? The idea is, frankly, genius. Instead of trying to punch through space and break the cosmic speed limit, which you can't do, you do something way cleverer. You basically get space-time itself to do the work for you. You create this little bubble of space around your ship. Then you compress the space-time in front of you and expand it behind you. It's like you're on a cosmic surfboard, riding a wave of space-time. The ship inside the bubble isn't actually moving, so no laws are broken. It's the universe that's moving around you.
So, if the idea is so elegant, what's the holdup? Well, the catch comes down to one guy and his unbreakable rules. We're talking about Albert Einstein. His theory of general relativity is basically the constitution for the universe. It sets the laws for gravity and space-time, and you don't just get to ignore it.
And you can really see how tough this is when you look at the timeline. Einstein lays down the laws of relativity way back in 1915, then crickets. For decades. It's not until 1994 that Miguel Alcubierre, who was famously a huge Star Trek fan, actually publishes a paper showing how it could work, mathematically. That gap of nearly 80 years, that tells you everything you need to know about how mind-bendingly difficult this problem really is.
Okay, so the real problem is baked right into Einstein's field equations. These are the mathematical rules that tell us how matter and energy bend spacetime. You've heard the analogy, right? Put a bowling ball on a trampoline and it creates a curve. That's gravity. Well, to make a warp drive, you need to create a super specific, really extreme curve, like a deep valley in front of your ship and a steep mountain right behind it. And to do that, well, that's where things start to get really, really weird.
Because to create that special wave in spacetime, you need something bizarre, something called negative energy density. This is a theoretical form of matter that would have anti-gravity properties. I mean, it would literally weigh less than nothing. It would push space away instead of pulling it in. And the problem is, this isn't just rare. We have never, ever seen it on any scale bigger than the tiniest quantum fluctuation. We're not even sure it can exist.
And hey, if needing impossible matter wasn't a big enough problem, there's another little headache: time travel. Yeah, it turns out that some of these warp drive models could accidentally create something called a closed time-like curve. Fancy name, but what it means is a pathway into your own past. And that just opens up a whole can of worms. You know, the classic grandfather paradox. What happens if you go back and accidentally stop your own grandparents from meeting? Physics really doesn't like these kinds of logical contradictions. So you start to see the picture, right? You need stuff that probably doesn't exist. The math is unbelievably complex, and you might accidentally break time itself. For decades, all of this just felt like an insurmountable wall. For human physicists, with nothing but their brains and a blackboard, it looked like a total dead end.
But what if we're not just using our brains and a blackboard anymore? What if we have a new kind of physicist on the team, one that can look at that wall and maybe, just maybe, find a door we never saw? This is where AI enters the story, and believe me, it is changing absolutely everything.
And it's so important to understand, AI isn't just a super fast calculator anymore. It's becoming a genuine creative partner. It's helping scientists to think in totally new ways, uncovering subtle patterns in the data that are completely invisible to human intuition. It's a huge shift from AI as just an assistant to AI as an actual participant in discovery.
So what can it actually do? Well, for one, we can use AI to run incredible simulations. Look, we can't just go out and build a wormhole in the backyard, right? But with AI, we can simulate millions of different versions of a warp drive. We can model what the chaotic, frothy foam of spacetime looks like at the quantum level. We can test all these wild ideas in a virtual laboratory to find out which ones actually have a shot at working.
And this is where it gets really powerful.
AI can take on those so-called impossible problems we just talked about. That massive energy requirement for a warp drive? AI can run optimizations and figure out designs that need way, way less. Those time travel paradoxes? It can analyze the logic and find solutions that are consistent. It can even help us dream up new kinds of metamaterials that could handle the insane stresses of manipulating space-time.
And maybe the craziest part of all is this. AI can do data-driven discovery. You can literally just feed it raw data from the universe, like telescope observations, and it can work backward to find the physical laws that govern it. It can spot the faint whisper of a gravitational wave hidden in mountains of noise. And here's the wild part. Sometimes, just by observing how things move, an AI can rederive laws we already know, like Newton's laws. It's like it's learning the source code of the universe all by itself.
But all of this leads to an even bigger, more radical question. What if AI's biggest contribution isn't helping us solve Einstein's equations, but helping us move beyond them entirely?
I mean, just let that sink in for a second. The idea that Einstein's field equations could become obsolete, that's huge. For more than 100 years, they have been the absolute foundation of modern physics. To think we might be on the verge of replacing them, that's not just an update, that's a full-blown revolution.
And this is the core of that new way of thinking. Einstein's view was geometric. He saw gravity as the curvature of a smooth, continuous fabric, space-time. But the new data-driven view that AI is helping us explore is totally different. It sees gravity as an emergent property coming from a deeper, more complex network of connections. It's less like a fabric and more like a cosmic computer network. A radical shift.
And this opens up a whole universe of weird and wonderful new possibilities. If space-time isn't a smooth sheet, then what is it? Maybe it's made of discrete, pixel-like chunks. Or maybe it's a fractal, where the same patterns repeat at every scale. AI can explore these bizarre, non-intuitive geometries, things our human brains can barely imagine, and see if they actually match up with reality.
So what this really means is that AI is helping us create a whole new language for physics. We're moving away from just writing down elegant equations on a blackboard. Instead, we're building these adaptive algorithms that can learn and evolve their understanding by looking directly at the universe. It's a language of data, of networks, of patterns.
Okay, so this brings us to the big picture. What does all of this mean for the future of discovery? Where is this new era heading?
This quote really nails it. For the first time, machines are not merely assisting in discovery, they are participating in it. Think about that. It's not just about having a fancier calculator. It's a fundamental change in the scientific method itself. Discovery is becoming a team sport between humans and machines.
And that partnership is what's so exciting. It lets us humans do what we're best at, being curious, being creative, asking the big, weird what-if questions. Then we can turn to our AI partners, and they can do what they do best, methodically explore millions of potential answers, sift through all the dead ends, and point us toward the ideas that are actually worth pursuing.
And really, that's the bottom line here. This whole journey isn't just about building faster spaceships anymore. The search for a warp drive has pushed us to ask a much, much deeper question. Is reality itself just a kind of pattern? A code that an algorithm can eventually learn to read? So I'm going to leave you with a final thought to chew on. If AI can potentially rewrite the laws of physics, these rules we thought were set in stone, what does that mean for our reality? If the very foundation can be changed, what else might not be as fixed as we think it is?